Good morning, good afternoon, good evening, and welcome to all of you joining our discussion from all around the planet. My name is Enrique Vieira, and today we'll investigate the heating and cooling impacts of a freshwater marsh and a glacial lake on a suburban weather station. I have been carrying this investigation with Professor Ali Nazemi, and we're glad to have you joining our discussion. On a global level, decades of climate change research conclude that nature-based solutions are a vital complement to establishing climate-resilient societies. Now, shifting from a global to a local perspective, we notice that nature-based solutions are already being implemented on the ground. For example, the government of Quebec has recently published Bill 132 in 2017, which strengthens the conservation efforts and recognizes wetland functions such as preventing excessive warming, and goes even further to enforce the construction of new wetlands. In conclusion, a deep understanding of wetlands and bodies of water is critical for their conservation or construction. We'll notice that the literature is asking for studies on the thermal effects of water bodies. According to Timothy Oakey, research on the urban heat island effect has started with Luke Howard in 1833, who compared urban and rural temperatures. In 1991, Oakey suggests that thermal properties and evapotranspiration play an important role in altering the surface energy balance. And apparently, most urban heat island research has focused on green spaces. And according to Kautz in 2013, the role of water bodies has received less attention. So this is one of the gaps our study helps filling. Then, recent works on water bodies mention the lack of station data, which we both have for the marsh and the lake. So let's take a look at our setup. First, let us situate ourselves in Canada. We are in the province of Quebec, near the border with the United States, in a city called Magog. Our marsh station is the green dot, situated in the Cherry River Marsh, which provides several ecosystem services to the city of Magog. Our lake station is the blue dot on a pier in Lake Memphremagog, which is a regulated transboundary lake with international implications regarding water quality and quantity. Environment Canada station in white provides hourly temperature data, and the two eddy covariance stations we maintained since March 2019 are shown on the right. We collect half-hourly data of temperature, relative humidity, wind speed and direction, precipitation, radiation components, surface level, and evapotranspiration, but the last one is not available in 2019 due to a manufacturing problem with a sensor. And now that you're familiar with our setup, let's start with the investigation. First, to quantify the heating and cooling impacts, we compute what is called the daily net degree hour difference, or NVHD in short, for the marsh and the lake, which is simply the sum of the hourly differences in temperature within each day, taken between the marsh or the lake station and the Environment Canada station. Second, to understand the microclimatological differences between the marsh and the lake, we compute the daily, weekly, and monthly difference in temperature, net radiation, absolute humidity, and vapor pressure deficit, and these four variables are selected because they're proxies of evapotranspiration and thermal properties. Also, we carry the analysis during full days and nights, because we know that evaporative processes and radiative processes change drastically at different times of the day. Third, we'll develop copulas to model the thermal impacts because they allow us to directly model the dependence of variables as well as their marginal behavior separately. And also, they can handle nonlinear dependencies and they don't require normalization. To do this, we first need to assess the dependence between different variables, such as the maximum, minimum, mean, or range of daily air temperature, to identify the best predictor using Mann-Kendall's method. For specific details on how to develop copulas, you can consult the reference below, and here I'll focus on some technical choices, such as having pre-selected the Frank, Gaussian, Student and Clayton copula families to determine which one is best. Lastly, we use the developed copulas to carry sensitivity analysis based on changes to temperature to assess the thermal impacts. In this first set of results, we have the daily net thermal effects in terms of NDHD by the marsh in the top row and by the lake in the bottom row, both on the reference station of Environment Canada in May to September of 2019 and 2020. We can observe that during the day, cooling is initially governed by the lake, but as vegetation grows on the marsh, both sites have a cooling impact. During the night, cooling is governed by the marsh, and we also see significant differences during full days. So let's dig further into these two microclimates to understand their differences. These are the weekly differences between variables of interest in the marsh and lake. The daily and monthly differences are not shown here simply to avoid an excessive amount of information. So during the day, net radiation is mainly governed by shortwave radiation and is lower in the marsh because the lake has a lower albedo and therefore absorbs more energy from the sun. As the growing season advances, the vegetation grows and temperatures increase, so we notice a higher absolute humidity in the marsh, which is physically consistent with its higher evapotranspiration. We can see that throughout the season, the vapor pressure deficit and the temperature difference decrease, and this is consistent with the higher evapotranspiration that we can confirm in the marsh through our preliminary evapotranspiration results that we get from eddy covariance. Here we can see clearly that during the day, the marsh in green almost always has a higher ET than the lake in blue. Also, the marsh's higher air temperature occurs because it has less capacity to store heat and readily releases it back to the overlying air while the lake stores it. However, we see that as the season advances, this warming is mitigated by evapotranspiration, which causes cooling and brings this temperature difference down to approximately zero. During the night, the marsh has higher net radiation, and we observe that our evapotranspiration proxies, vapor pressure deficit and absolute humidity, both indicate a higher evaporation in the lake, which makes sense from a physical perspective because evapotranspiration in the marsh is minimal due to the lack of photosynthesis and near zero wind speed at the surface due to the dense vegetation. So that induces evaporative cooling to be higher in the lake, which we can confirm by our preliminary eddy covariance results. As we can see in this graph, that the blue line is always superior to the green line. However, realize that if the lake is receiving less net radiation and evaporating more, but its temperature is still higher, this heat must be coming from the heat storage and the heat storage of its immense mass of water. So let's investigate this further. During the night, only long-wave radiation changes significantly between sites. We see in this figure that as the growing season advances, the lake radiates back more and more outgoing long-wave radiation in comparison with the marsh. And according to Boltzmann's law, outgoing long-wave radiation is a direct function of the temperature of the medium. So this graph shows that as the growing season peaks, the lake has more stored heat than the marsh. But let's verify this from another angle. We also observe in hourly averages that the lake has higher thermal inertia and slower radiative responses. First, we can notice that while the peak in incoming shortwave radiation occurs simultaneously in both sites, that is, the black solid and dashed lines, the response in outgoing long-wave radiation is slower and later in the lake in blue compared to the marsh in green. We observe that the lake's outgoing long-wave radiation has a smaller amplitude than the marshes, which shows that it's harder to change the lake's temperature in comparison with the marshes. Now that we better understand the landscapes, let's model the thermal impacts. First, we did some basic statistical analysis on temperature minima, maxima, and range, and the net degree hour difference. Here we show the temperature range because it was selected as the best predictor according to Mankendall's method. We can see that in the marsh, the distributions of the temperature range and the NDHD are not normal, which makes copulas an excellent choice for modeling them. We can also see that their quantile plot shows that the 2019 and the 2020 data follows a very similar behavior. So we'll combine the data from these 2 years to build the monthly copulas. In the lake, we see a very similar message, which you can explore for some time by pausing the video. Then, we use the combined data from the 2 years and we discover that it is the temperature range which displays the best dependence with NDHD, but it's only statistically significant above 90% after July, possibly because of the vegetation's maturity. So we'll model the thermal impacts in July, August, and September for both sites. The Frank copula family had the best performance, so it was selected for modeling. On this color map, we see the modeled thermal impacts of the cumulative distribution function of the NDHD on the y-axis and the different changes in temperature range in the x-axis. The first row shows that in the marsh, as we move from 0 toward -5 degrees of change in temperature range, we see that the mean of NDHD becomes cooler, as well as the upper percentiles of the distribution. Also, in August, we see cooler values at the lower percentiles as well. The second row shows that in the lake, moving toward negative changes in daily temperature range also results in a shift of the thermal impact distribution toward cooler NDHD. Therefore, we can conclude that the heating and cooling impacts of the marsh and lake are overall most sensitive to negative changes in the temperature range, which in both distributions are associated with a shift toward cooling impacts. Also, reputable works in the literature have identified that the daily temperature range is increasing due to climate change, in which case the marsh and lakes cooling impacts will be even stronger. In retrospect, we should remember a few takeaways from our investigation. First, that the heat storage plays a critical role in temperature regulation. Second, that in the marsh, vegetation's effects are so strong that they shift the heating in the spring into cooling during the summer. Third, that the lake acts as a temperature stabilizer, since during the day it provides cooling and during the night it provides heating. And lastly, from our sensitivity analysis, we can conclude that marshes and lakes will play an even more important role in cooling as daily temperature ranges decrease with climate change. Thank you for your attention, and I'm looking forward to discussing with you during the live session.